Hello everyone, so today in this video we're gonna look at the problem which is called adiabatic flame temperature. So let's say we have a burner and we are burning a natural gas, let's say, and we are burning it in air, in excess air, which is like 20% excess air, and we are asked to determine 20%. And we are asked to determine the flame temperature, and we are assuming this burner to be adiabatic, which means there is no heat loss at the walls, which means the enthalpy of the reactants that are coming into the reaction must be equal to the enthalpy of the products that are leaving the burner, and we're assuming that the kinetic energy of the products and the reactants are going to be the same or negligibly small, so that we're not taking it into account and the height differences, so we're not also concerned about the potential energy. So we're given the natural gas. So natural gas consists natural gas consists of 95% of methane, and 4% of ethane. And 1%, and all the percents are in mole, so they are mole percent of propane. And we're burning it in air, and the air consists of 79 mole percent of nitrogen and 21% of oxygen. The actual mole percents are actually like 78 to 21, and there's 1% of argon, and we're not really taking that into account now, so that to make our problem much easier. Okay, and we are saying that as our burner is adiabatic, we're saying that enthalpy that is coming in must be equal to the enthalpy that is leaving out of the burner, right? Okay, and as our natural gas is burning, we might write the combustion reaction for methane and ethane maybe to see what's really happening. Okay, let's say CH4 methane is gonna burn in oxygen, and we also have the nitrogen, right? The nitrogen is not gonna be involved in the reaction, and so we're gonna have nitrogen in both at the beginning of the reaction, at the end. So we're gonna write nitrogen, and the mole ratio for nitrogen is 79/21, which depends on the mole of the oxygen. Okay, so we're gonna have carbon dioxide and plus water plus, oh, I think there's no enough space, so let's kind of move this a bit. Okay, and plus nitrogen. Okay, we should not forget the mole ratio of nitrogen. Okay, now let's try to kind of make the both sides equal to each other. Okay, so the number of carbons at both sides are equal to 1, right? So we're gonna leave it as it is. So, but the number of oxygens, so if we kind of put 2 here, we can make this equal to 2, and the number of hydrogens is also 4, and number of oxygens are also 4 in both sides. So as we said, the nitrogen is going to depend to the mole of the oxygen. We're going to put 2 next to the nitrogen. So this is our first reaction, and in our second reaction, the ethane is reacting with oxygen, and we still have the ratio of nitrogen to oxygen, and the products are going to be the same: carbon dioxide, water, and nitrogen. And if we're gonna balance this reaction, so the number of carbons on the left side is like we have two carbons on the left side, so we're gonna put two here, and so the number of hydrogens is 6, so we're gonna put 3. So the number of oxygens are 4, 3, so 7, and so we don't have to make the coefficients as a integer, so that we can leave it as 7/2. Okay, so as the mole of nitrogen is depending on the oxygen, we're gonna just put 7/2 to here and 7/2 to here. Okay, so what is our next step? So we said that we should be working with the enthalpies, right? The enthalpies that are going in must be equal to the enthalpies that are going out of the burner, so that we can kind of find the actual temperature. And we know that the enthalpy, so delta H, is equal to the like specific heat constant and times change in temperature. So in their standard states, the compounds are going to have the coefficient to be equal to 0, because, so for example, we have in our reaction we have oxygen and nitrogen, so initially their specific constants are equal to 0, but we cannot assume that specific constant is going to be constant throughout our reaction, as when we go to the higher temperatures, the temperature is also going to affect our specific heat constant. So we should kind of use our CHE tools that we use in our previous videos, which is a computational tool to calculate all the properties of the compounds. So we're going to use CHE tools that can calculate the specific heat capacity for the compounds, but the CHE tools uses equation 107 from ChemCAD. So in order to find the change in temperature, we should kind of integrate that from lower to higher boundary, and that equation that ChemCAD, that CHE tools uses, is y is equal to a plus b times specific c over t. So we have a, b, c, d, and e. No, yeah, a, b, c, d, e to be our coefficients, and we're gonna get that numbers from our CHE tools. So hyperbolic sine c over t to the squared plus d e to the e t over cosine hyperbolic e over t squared. So this is going to be our equation to calculate the specific heat constant. As I said earlier, we should take the integral from that. So what we're going to be using is, so we can use Wolfram alpha to calculate our to get our integral. So if we take integral respect to t, so we can take integral from this and this parts like separately, so that we don't kind of mess everything by writing all the equation to Wolfram alpha. So when we take the integral from a, it's going to be a to the a times t, right? So now let's try to take the integral from this part. Okay, we go to Wolfram alpha, and so in So it's going to be integral of, so we have 4c over t divided by hyperbolic sine it's going to be c over t and times, so it's going to be raised to the power squared, right? So we're taking that respect to t, right? So if we calculate that, so here we have our answer. So it's going to be c over, so it's going to be c over hyperbolic cotangent. So we're going to, so hyperbolic cotangent is, we can express it as 1 over tangent, right? So it's going to be b multiplied, of course, so it's going to be b times c over, so over tangent, hyperbolic tangent, and it's going to be c over t, right? So minus, so now we have to take the integral from this part, from the last part. So I'm going to just change the part that I need. So it's going to be e, and this is going to be cosine hyperbolic, this is going to be e, and we're taking it with respect to t. So it's going to be negative e tangent, hyperbolic tangent e over t, and this e is a constant, right? So I'm going to write it as e times g tangent hyperbolic e over t, right? So now we have our equation to take the integral. Now we can write the Python code to determine the specific heat constant for a specific temperature. And what we can do is we can use the root equation from SciPy Optimize to actually find the point, specific temperature, the point at which the enthalpies that are coming in must be equal to the enthalpies that are going out. So to do that, we should write the Python code in Google Colaboratory. So we're going to use this equation that we just obtained. So now we are in the next step of solving our problem, which is writing a Python code. So before we start our code, we should import some important libraries to our Colaboratory, which is, so we need CHE tools as always. So as we're working with some compounds, we need to get the properties of the compounds. So we're going to be using CHE tools from our GitHub website. So we import it here with using git clone. And so we're also going to import numpy and also SciPy Optimize. So we're going to be using the root solver. So we're going to import the root function from SciPy Optimize library. Also, and here we're just importing CHE tools as CHE. Now we can start with the coding process. Okay, so as we are working with the compounds, we can just get the properties of all the compounds as P. So G dot props, and we need to have an array. We need to have an array for all the compounds. So what compounds do we have? We have methane, right? And we have ethane. We have and propane, right? What else do we have? So we have oxygen and nitrogen. We have oxygen and nitrogen, and we should remember the order. Later, while we code, we might need to use this order. So then after nitrogen we have carbon dioxide, right? So carbon dioxide, and the last thing is what? We have water. We have water. Yes, let's just control shift and so there is a propane, there is a typo, and then oh sorry, there is a propane. Yep, working good. So what is the next step? So the next step is gonna be to use our integration equation to calculate the enthalpies that are coming in and the enthalpies that are going out of the reaction. So let's just define a function, integrate, so that will return the integral. Okay. Okay, so it should return the integral. So as I mentioned before, we have the constants A, B, C, D, E, right? That we're gonna take that from CHE-tools, and that constants are gonna be P dot C, C I, C P, C P I D A. Okay, let's just check that before we actually run it. Okay, P dot CPI CPIGA, right? Okay, let's just run it. Name P is not defined. Oh, here I see. I use a capital P here, and now it should work. It should work now. Yeah. So you see, here are we getting A values for all the compounds we have. So these are the constants that will determine the specific heat constant at a specific temperature, right? Let's just return our integral. Okay, so it's times times t, right? So this is our first term plus what? So it's gonna be plus p dot cp cpigb. So it's b times p dot cpigc over numpy hyperbolic tangent, and that's gonna be p dot cic over t, right? So this is our second term, and our last term is p dot ci, so that's e times p dot ci, so p times d, right? And times numpy hyperbolic tangent, and that's gonna be inside, so it's p dot ci e over t. Let's just run that. Here we go. Okay, so what's the next step we do? So now we can have another function that will calculate the, so here we said that we calculated our specific heat constant, right? But the enthalpy is specific heat constant at a temperature, at a specific temperature, right? So now we have to calculate the enthalpy. So we can have like function called h that will take the value of our temperature, and it should return what? So here if we go here, if we say so from our CHE tools, we can get the heat of formation for ideal gases, right? So it's here we're kind of getting all the heat of formations for ideal gases for the compounds here. If you notice, we have 0, 0 for oxygen and nitrogen because they are in their standard forms, like they're in a gas form, so they have the enthalpy of like heat of formation of 0. So we can use this heat of formation, and we can kind of add our integrate uh, values. So what we are doing is we are finding the difference between two integrals, right? So we said that the enthalpy change is going to be the difference in like from the upper boundary to the like from lower to the upper boundary. So our lower boundary is 298 kelvins, and so we're integrating it until the T, which is going to be the our temperature that we need to solve for. So let's just run this function. So now we have two functions, the integrate and the enthalpy. Now what we do is the next step, we can kind of work with the moles, so that as like with the mole ratios and moles, so that we can find the enthalpy for specific mole. Let's say let's have an array for our compounds that are burning. So we have methane, ethane, and propane in different mole ratios, right? So let's say and fuel is going to be equal. So we should create an array for that what I mean for the mole ratios. So it's going to be 0.9895, right? 0.04 and 0.01. So now we have an array. So now we have an array for the mole ratios of the compounds, and now we are also given in the question that we have an excess air. So we should need to specify that it's going to be 0.2. So we have 20% of excess air. And what else do we have? So we have, so in our fuel, we have different ratios of carbon to hydrogen, right? So we can use that to calculate the standard heat of formation for the compounds in order to calculate the initial enthalpies of our compounds. We need to specify the mole ratios of the compounds. So in methane it is 1 to 4. So we're going to have 2D array for each of our compounds. So 1 to 4, that's going to be the first element, and then we have 2 to 6, that's the second element, and we have 3 and 3, I forgot, 3 to 6, 3 to 8, right, for the propane. So these are going to be our, and I need to have the bigger array, so 2 here. So now I have 2D array that represents the carbon to hydrogen ratio of each of the compounds in our fuel, right? And now we have to do the matrix multiplication with that. So we have to multiply the compound, so the mole ratio, to the carbon hydrogen ratio. So what we to find the actual moles of carbon and hydrogen. So what we do is, so we can do the like matrix multiplication with fuel CH, and make that equal to the moles of carbon and moles of hydrogen. And the next step we should do is, um, we have the carbon, so we are going to be having the carbon dioxide and the right hand side of our reaction, right? And that's going to be the same mole as our carbon here, right? So in both of the equations we can see that how many carbons do we have on the left side, and that's the number of carbon, that's the mole of carbon dioxide we're going to have on the right hand side of our reaction. So we're going to have CO2, so mole CO2 is going to be equal to the mole of the carbons that we determined with the matrix multiplication. So mole of H2O, so what is that equal to? So it's equal to the mole of hydrogen divided by 2. So here we have 4, and here we have 2 moles of water. Here we have 6 hydrogens, and here we have 3 moles of water. So we're going to have NH over 2, right? So the next thing is the oxygen, right? So the oxygen is going to depend on the amount of mole. It's going to depend to the mole of water. So it's going to be the amount of water divided by 2 plus the mole of carbon dioxide, because that's the number of oxygens we have here. So we have mole of H2O divided by 2 and plus, so what else? So I said like carbon dioxide, right? So it's going to be NO2 and CO2. And as we have an excess air, we should multiply that by 1 plus the excess air. And here, why is that showing an error? Oh, there is a typo here. Okay, the last thing we're left is the mole of nitrogen, right? So to find the mole of nitrogen, what we should do is, so it's going to depend on the mole ratio, on the mole of the oxygen, right? And it's going to be multiplied by 79 over 21. So we can have 79 over 21 multiplied by the mole of oxygen. So if we increase the amount of oxygen, the amount of nitrogen is going to increase automatically. So it's going to be dependable. Okay, let's just run it. Here we go. Now we have all the moles of our compounds that are reacting, of our fuel, of the oxygen and nitrogen, of carbon dioxide and water. So now we should do the array multiplication to find the everything that is going in and everything that's going out. So let's say moles that are going in. So we can, in NumPy there is a function called concatenate. Yes, this function. So this does the matrix not the matrix multiplication, but array addition. So what do we do here? So we should need the amount of fuel that's going in, right? And with the numpy array of what is going into our reaction. So the fuel, and another array we're gonna have is for the oxygen, right? For the nitrogen, I think I forgot the parentheses here. Yes, it should be fine now. So, and then amount of nitrogen, and then we don't have carbon dioxide and water and first side of like in the right hand side of our equation, right? So this is where I said like the order matters. So as we wrote down the carbon dioxide and water as the last, we can just kind of make their moles equal to 0. Okay, now this is the moles, all the moles that are going in, and now we should have another array that for the compounds, for the amount of compounds that are leaving our burner. So we're gonna create an array. We don't have to do the what is that? The we don't have to do the array addition. So we don't have all the 3 compounds like methane, ethane, propane, and on the right hand side. So we're gonna make the moles equal to 0, right? And we have oxygen because of the air, right? We have excess air, so we're gonna have NO2. So the excess of air that's left times excess air. And so we have the nitrogen that's gonna leave our reaction, and we have carbon dioxide and water. So it was H2O. Oops. Oh, this should be fine now. Let's try to run it. Yes. So now we have 2 arrays for the amount of compounds that are going in and for the amount of compounds that are going out of the reaction, like of the burner. So now we have to find the enthalpies, right? So in order to use the root solver, we should have a function to that we have to take like put into it. So our function is gonna be the difference between enthalpies that are going in and the enthalpies that are going out. And let's say like uh, different, let's say it's like equation that's gonna take a vector, right? It should take a vector. Our vector is gonna be the temperature. And it's gonna be the first element of the vector. And it should return the value for, so it should return the value for the difference in enthalpies, right? So we're gonna return the difference in enthalpies as an array. So it's gonna be, so now we should do the we should find the dot product of the amount of compounds and the temperature. So in NumPy there is a equation NumPy dot dot that calculates the dot product um, of the of 2 things that we need. So we need to calculate the enthalpy and multiply it dot, like find the dot product of it with the what, so with the amount of it. So we're gonna have enthalpy function, right? That's taking T multiply and amount of compounds that are going out. So this is going to be the first part of our equation. So as we're working with the difference, we should find the enthalpy that is going in. So it's going to be H. So we're assuming the compounds are entering the burner in standard room temperature. So it's going to be the enthalpies, standard enthalpies, and room temperature multiplied, not the multiplied, but it's going to do the dot multiplication. So, and that are going in, right? Let's try to run it. So it's working. Now we can do the last step of our solving. So our root solver from SciPy Optimize should take the function equation right? And we should provide the initial guess. Let's say our initial guess is 2400 degrees Kelvin. Let's try to run it. Oh, here we go. It's running, right? And now we should isolate the answer that we need. So we're gonna get the x, the first element. Let's try to run it. So looking back to our to code, I noticed a typo error here when we were writing our integration function. That was resulting us to get the wrong number. So now if we run all the code, we can have the actual number, actual result, which is going to be 2063.7 kelvins. So thanks for watching our video. I think you find it helpful. Thanks for your attention.